All right, now in the previous video, we showed how to use row operations to reduce an augmented matrix into a form that corresponds to a system of equations that's easy to solve. What we didn't explain is why we use this sequence of row operations. So in this video, we're going to talk about a systematic way of using row operations to reduce a matrix into a simple form that enables you to read off the answer. Furthermore, we're going to talk a lot about this simple form called reduced row echelon form because it's going to form the basis of a lot of our future discussions. Notice in particular that this form, this system of equations, it's not immediately obvious what the solution is. You still have to do some further work. But if you have a matrix in reduced row echelon form, you can immediately see the solution without any further work whatsoever. Okay, so let's get started with that. Here's the definition of reduced row echelon form. So this is the form that we're going to change our matrix into for any augmented matrix. Okay, so first condition. If there's a row where every entry is 0, then this row lies below any other row that contains a non-zero entry. So all 0 rows at the bottom. Number 2. The leftmost non-zero entry of a row is always equal to 1. Okay, so if the row has any non-zero entries at all, the first non-zero entry is a 1. Number 3. The leftmost non-zero entry of a row is the only non-zero entry in its column. So for instance, if I have a matrix here, and I have a leftmost 1 here, which would mean I have zeros here, that means that all of these are zeros as well. Okay, it may not be 0 back here, may not be 0 up here, but if there's zeros here and a 1, then all of these are zeros as well. This one says, consider any 2 different leftmost non-zero entries, one located in row I, column J, the other located in row S, column T. If I S greater than I, then T is greater than J. What that means is that if I have a 1 below, if I have a leading 1 below this one, then that leading 1 has to be to the right. If I have a leading 1 above this one, then it has to be to the left. That's all this means. I call this a stair-step pattern. Right, so the ones go down like this, they go down and to the right. You could make stairs like that. And remember, whenever you have a leading 1, you have zeros everywhere else in that column. So if I have 1 here, these all have to be zeros. Okay, so so zeros at the bottom, leading 1s in every row that has non-zero entries, and stair-step pattern, and columns all 0 for those leading 1 entries, and stair-step pattern of 1s. All right, so if you didn't get it from that description, we'll see many, many, many examples of matrices in reduced row echelon form. All right, so whoops, sorry. Let's get this back here. Didn't do that. Okay, there we are. All right, so the leftmost non-zero entry is called a leading 1. A column containing a leading 1 will be called a pivot column. A pivot column. The leading 1 itself is called a pivot. The number of non-zero rows will be denoted by R, which is also equal to the number of leading 1s and the number of pivot columns. Why is that? Because each non-zero row has a pivot, has a leading 1, and each leading 1 produces a pivot column. Pivot column, remember, is a column that has only 1 entry that's 1, and all other entries as 0. Okay. So the set of pivot column indices for pivot columns is denoted by D, and the columns that are not pivot columns will be denoted by F. Okay. So D is a set of numbers, F is a set of numbers. Altogether, D and F will give the numbers from 1 to N. Where in this case, N is equal to the number of columns. Okay, so each column is either going to be in the D set or the F set. Okay. So here he repeats the thought that I said, is that the ones form a stair-step pattern. Okay. So let's go down to these new terms and definitions. And here he makes the point that these terms apply to any matrix, whether it's an augmented matrix or a coefficient matrix. So you need to be careful and always consider whether you're analyzing a coefficient matrix or augmented matrix, but these concepts can apply to either one. You can reduce row echelon a coefficient matrix or an augmented matrix. All right, so here's an example. The matrix C is in reduced row echelon form. Why is that? Let's identify the 0 rows. They're at the bottom. Then we identify leading ones in every row. Those leading ones all have zeros everywhere else in their corresponding columns. And the ones form a stair-step pattern. Okay, so it meets all the conditions that we have for reduced row echelon form. Let's go down to the next one. Now this one is not in reduced row echelon form. Why not? Let's check our conditions. First of all, leading rows. 0 rows. Here's a 0 here. Here's a 0 row here. It's not at the bottom. So this is not in reduced row echelon form. However, if I took out this row, let's see if this is still in row echelon form. Suppose I erase this row. It's not there. Is this matrix now in reduced row echelon form? Well, let's check our other conditions. Our 0 rows are at the bottom. Let's look at leading ones. Leading one here. Whoops, no leading one here. No leading one here. Not reduced row echelon form. Okay. So suppose I take out this one here. Suppose I remove this one. Let's see if this is now reduced row echelon form. All right, so here we've got a leading one here, leading one here, leading one here. Okay. Now we need to check that for these leading ones, every other entry in the column is 0. All zeros here, all zeros here. Remember, these two are gone. Forget about those. All zeros here. All zeros here? No. Okay. But if I change this to a 0, then we'd be okay. All right. So the matrix that I've doctored up here now has reduced row echelon form. All right. So let's go to theorem REMEF. So suppose A is a matrix, then there is a matrix B, so that A and B are row equivalent, and B is in reduced row echelon form. So I can say that any matrix can be put into a reduced row echelon form by means of row operations. Okay, I can use row operations to take any matrix and put it into reduced row echelon form. And the procedure for doing this is called Gauss-Jordan elimination. Right now, in the book, there's a long discussion about how to do this process of Gauss-Jordan elimination. Here's a description. And down here, they explain the different steps. Here's a computer code, which really shows you that you can do this process. And what this description and this computer code are really a distillation of a procedure. Now, I think it's a little bit difficult to read through the description and the computer code without understanding the procedure. So the best thing to do is to simply describe the procedure, and once you get used to the procedure, then the discussion and the computer code makes sense. So that's really how the discussion in computer code came about in the first place, people doing this many times and seeing the pattern and systematizing the pattern. So let's just skip down to the examples. And I'll come back and talk about this reduced row echelon form is unique. in a minute. All right, so here, let's look at some examples. All right, here's an example. Now, I have, for my own purposes, I've described the steps that I would say are useful in following when you're doing reduced row echelon form. So first of all, first thing you want to do is create leading one. So you create a leading one. So I should say in the first row possible. Okay, we're going to be working our way down. First you create a leading one in the first row, and then keep on going. And eventually you'll run out of leading one. So first you create a leading one in the first row possible. Then you make all zeros below it. Then you repeat steps 1 through 3 until all leading ones have been made. So you cycle through these 3 steps. Make a leading one, make zeros below it, then go on to the next row, make a leading one in that, make zeros below it, and so on. You're still not done. Then finally you have to use those leading ones to create zeros above them. Okay. This is a sketchy description, but you'll see how it works in the process. And as I said, to understand this process, you just do many, many examples, and you'll see how it works in general. All right, so here's a system of equations. Here's the augmented matrix. So I said, first of all, we want to create a leading one in the first row possible. So we can create a leading one in the first row. There's no problem with that. That's what he's saying, j equals 1. That's the first row. All right. So my leading one is going to be here. Right. Now, one way to put a leading one there would be to multiply the first row by minus 1/7. That would work. But we can see from here that an easier way would be take the third row and move it up. So that's what he does, is take the third row and move it up. So we have our leading one. Once we have our leading one, we want to zero out all of the entries below that leading one. So that explains these next 2 row operations. I have my leading one in the first row, first column. I do the first row operation, makes this one a 0. Second row operation makes this one a 0. And this is my pivot entry. All right. So I've gone through one cycle of steps 1 through 3. Create a leading one, make the zeros below it. Whoops, sorry, it skipped. And repeat steps 1 through 3. Okay, so now I have to go to my next cycle, repeat those steps until all leading ones have been made. All right, so let's go to my next place. Where can I make a leading one? Well, I can make a leading one here. Right. The way to do that is divide that second row by 5. So that's what we do here. Once I've created that leading one, I need to make all zeros below it. So that explains why we do this row operation to zero out the entry below the leading one. Now, it just so happens that this has a 0 above it. That's not always going to be true, but that just so happens to be true. All right. So I have my first leading one, second leading one. Let's go through the cycle again. I want to make a leading one in the first row possible. That's right here. I can make a leading one right here. Easiest way to do that, multiply this row by 5 halves. If I multiply the row by 5 halves, I have a 1 here. Okay. Now, can I create, there are no rows below it, so I can't create any more zeros below it. Can I create any more leading ones? The answer is no. I've run out of rows. Okay. All right. So now what do I have to do? Now, according to my step 4, I'm going to use the leading ones to create zeros above them. So this leading one is okay. There are no rows above. This leading one already has zeros above. This leading one needs to have zeros above. So I need a 0 here and a 0 here. Right. So to get rid of this minus 13/5, I can multiply the third row by 13/5 and add to the second row, and that will put a 0 here. Now I will want to get rid of the 4. To do that, I can take the third row, multiply by minus 4, and add to the first row. Okay, so then I have my leading ones. Right? So let's see. Is there anything more we can do? The answer is no. I have a leading one in every row. Each leading one corresponds to zeros in that column and every other entry, and the ones form a stair-step pattern. All right. Now, nice thing about this is that you can read off the solution from this form. We know that the first three columns correspond to variables x1, x2, and x3. So this first row corresponds to the equation x1 equals minus 3. Second row, x2 equals 5. Third row, x3 equals 2. You can see this is the only solution because that's what the equations are. x1 equals 3, x2 equals 5, x3 equals 2. There are no other possibilities for x1, x2, x3. All right, let's try another one. Go through the same process and see if you can get this down. So here we have a matrix here. The system of equations here, we create an augmented matrix. Okay, so what do we want to do? We want to create a leading one in the first row possible. That's right here. That means that we have to zero out this entry and this entry. Zero out this entry, add minus 2 times row 1 to row 2. That zeroes this one out. To zero out this one, add it minus row 1 to R3. That zeroes this one out. My first pivot column is done. All right, let's go and create my next leading one. Where can my next leading one be? That's right here. Okay. We can simply multiply that row by 1/3, make it a 1. Then I want to zero out all of the entries below it. To zero out all of the entries below it. Now, see, he does it in a slightly different order. You can do it in that order, but I think it's systematic to do the ones below and then go back and do the ones above. You really can do it any way you want to. Okay, so he took this one and he eliminated the 0 up here, and then he eliminated the 0 down below. So you can do that as well. Now, at this stage, what can I do? My next stage is to create another leading one, but there's no possible leading one to put in this row. These are all 0 entries. How can I get a 1? No way. Okay? So I'm done with that process. Then I can go back and create leading ones above, but I'm going to create zeros above all the leading ones, but there's no entries to take care of. So I'm all done. I'm all done. Let's check that this is in reduced row echelon form. This leading one only has zeros in the column in other entries. This leading one only has zeros in other entries in the column. And the leading ones form a stair-step arrangement, so I'm all good with my reduced row echelon form. All right. Now, in this case, these correspond to what system of equations? Well, this is x1 plus x3 equals 3, x2 plus minus x3 equals 2. All right. So, this does not have a unique solution. In fact, for any value of x3, I can get a x1 and a value of x2. So in fact, I can get a solution for x1 and x2 in terms of x3. x3 is my free variable. x1 and x2, these are my pivot variables. So notice that x3 corresponds to a column that is not a pivot column. That's going to be true in general. Free variables will correspond to columns that are not pivot columns. Okay, so let's go down and look at this description. So what he does to get x1 and x2 in terms of x3, he puts the x3 on the other side. So you put the free variables on the right-hand side, and the pivot variables are expressed in terms of the free variables. Once you do that, I can write a solution set. x1 is expressed in terms of x3 as 3 minus x3. x2 is expressed in terms of x3, 2 plus x3, and x3 can be arbitrary. Okay, so I have this set, which is an arbitrary set, which is a set of different solutions, and in fact gives all the possible solutions for that system of linear equations. All right, let's see if we have one more example. All right, let's look at this one. System of equations. Convert to augmented form. I want to make this one a leading one. Make this one a leading one. Simplest way, move the 1 up. Okay? Move the 1 up. I want to zero all the entries below it. So he zeroed out. You get the 1 out. Zero out this one. Zero out this one. Took care of this. Took care of this. Okay? I want to create another leading one. Bunch of ways to do this. Whoops. Sorry. Skipped down too far. Back there. Sorry. Have to be very precise here. All right. So where are we? Okay. I guess it's the next page that skips around. All right. We want to put a leading one in this entry, and let's go down to the next page. I think it's skipping from the page. All right. So what he did was he exchanged these two rows because it's easier to work with a -1. He exchanged these two rows and then multiplied by -1. So he's got his second leading one. So what do we want to do? We want to make these two 0. Now he does it in a slightly different order from the way I described. He zeroes out all of the entries above and below that that leading one using row operations. You can do it that way as well. So he zeroed out the entry above and he zeroed out the entry below. Now I have to repeat my process. I want to create the next possible leading one. Where's the next possible leading one? That's over here. Okay. I create that leading one just by multiplying the last row by -1/5. So I have a leading one here. Then I need to make all zeros above it. So this one's already a 0. I'm to make this 2 a 0. I take row 3. I take -2 row 3 plus row 2, and I get a 0 here. Is this reduced row echelon form? I have no 0 rows. I have leading ones in every row. Each leading one has zeros everywhere else in that column. Okay, so let's think about what equations this corresponds to. Remember, this is an augmented matrix. These are variables x1, x2, x3, x4, and this is a constant column. So let's think about this last row. What equation does this correspond to? Well, 0x1 plus 0x2 plus 0x3 plus 0x4, that's x3, sorry. 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1. In fact, that last row corresponds to the equation 0 equals 1. This is patently false. It's impossible. So there's no solution. No solution. Okay. If the last column is a pivot column, there's no solution. Because if the last column is a pivot column, that corresponds to an equation 0 equals 1. So he describes the solution set as the empty set. Okay. So in fact, these three examples represent all the possibilities. You can either get one solution, infinitely many solutions, or no solution. All right. So hopefully you see this procedure, and you can see how to do this in general. And I do want to skip back to the point that I missed, namely that every matrix has a reduced row echelon form. So let me go back here. And he says, sorry, just give me a second. Okay. So let's just read the formal statement. Suppose that A is an m by n matrix, so A can be any matrix, and B and C are m by n matrices that are row equivalent to A and in reduced row echelon form. Then B equals C. All right, so this says that for any matrix, when you row reduce it, there's only one possibility. It can't row reduce to two different row echelon forms. In other words, each different row echelon form is distinct. You can't reduce one row echelon form to another row echelon form. Now he gives a formal proof of this, but I think the best way for you to convince yourself is to see that this one process is always going to end up in the same result. You're always going to get your ones in the same place, and once you have the ones set, then the zeros are set. Once the zeros are set, then all the other entries are set. All right, so you can go through the formal proof, but that is the gist of this theorem. Now the other theorem that is up here is that every matrix in fact does have a reduced row echelon form. And what you're just saying is that you can do this process on any matrix at all. Okay? So any matrix has a reduced row echelon form. It has only one reduced row echelon form. However you get there, you'll always get the same reduced row echelon form. Okay, so that's it for this section.